Thank you very much, and it's a special honor for me to give the first morning talk after the conference dinner. I'd like to take minutes for organizing it in such a special place and actually for organizing the conference itself in this very wonderful location. I'm going to give some overview of what we've been doing in Sofia in the last few years. I decided to go for an overview rather than for a specific topic because I guess it's not so often that you hear talk from Bulgaria. Three topics I will cover. It's about composite pulses, a very powerful but not so popular method of quantum control, then some results closely related on dynamical decoupling and pulse shape effects in the end. Now, briefly, what are composite pulses? They, as shown here, flatten the excitation profile on the top of a Rabi oscillation when driven by resonant pulses. We know that it's quite sensitive. Composite pulses really make it very robust. They are advantageous to compare to adiabatic evolution, which is very robust to experimental errors, but it's not very precise. Composite pulse is actually a sequence of pulses. It's not a single pulse, but a train of pulses with very well chosen phases. So each pulse has a phases. The pulses here are identical. They don't have to be, but usually they are identical. And these phases have to be controlled quite well, and they are used as control parameters. So the talk today is about phase control, destructive and constructive interference. Composite pulses have quite a bit of history. They were invented in NMR in the 1980s. It turned out they were known in polarization optics, the mathematics, much earlier than that. One of the main contributors in polarization optics is Steve Harris, is the same person who invented EIT. And in quantum optics, they were introduced by Rainer Blatt in the beginning of 2003. I understand from him that this was a result of a visit of Ike Chuang, one of the big names in NMR quantum computing, to Innsbruck at that time. And Christoph Wunderlich is another figure that contributed very much to the popularization of this control tool. Now, what we did in this very old method, not very old, well, for me it's not so old, but for most of the audience it's quite ancient, was to change the approach, because we were much more used to use the SU2 rotations and SU3, SU4, etc. While in NMR, it's all about the block vector and the block sphere, which is SO3. And it turns out that computers like complex two-dimensional matrices much more than real three-dimensional matrices. So we were able to go much further than before. And I'll show you pictures. So basically, the propagator of a two-level system of a qubit looks like this. A and B are Cayley-Klein parameters if we're fully coherent. This is the case when we put a phase on the field, a phase shift on the Rabi frequency, E to I phi, it goes here off the diagonal of the propagator. And when we have a sequence of pulses with different phases, this is the overall propagator. It contains a number of phases, and if these phases are free parameters, you can control the propagator in a variety of ways. And actually, it's a very powerful control tool. Now, there are three types of composite profiles. One is broadband, which is the most popular one, and I'll mention it briefly, but I'll focus on the narrow band, which creates very delta function-like structures in the transition probability. The dashed line is the traditional Rabi oscillation, so we can expand the profile or squeeze it, or you can make it passband. You can have flat top and flat bottom, which also is quite interesting. Or you can lock the transition probability somewhere in between, for example, at 1/2. And in this way, you can have a Hadamard gate, which is very robust to experimental errors. Now, briefly about our earlier work on composite pulses. I was here 2 years ago on the Humboldt Colleg conference, again organized by Gediminas. I spoke a lot about these pulses, so I'll mention them only briefly, but I'll focus on something else. So broadband composite pulses have this very broad top. We were able to develop analytical expressions for the pulse shape, which depend on which apply to any number of pulses n. And the k is the running index, which labels each pulse. And here are a few sequences. The first one was well known in the 80s from NMR, but all the others were quite new. And the transition probability is given by this expression for these sequences. And this cosine here when you take powers, higher powers, it goes to 0 unless it's equal to 1 or minus 1. And then the profile really flattens and tends to 1. And these are profiles from for 1, 3. This is the Rabi oscillation. This is 3 pulses, 5 pulses, and so on until 45. And you can see that you can have as much as 80% deviation in the pulse area. 80% error can be compensated by composite pulses, which cannot be done by any other technique. And all this compensation happens at a very low rate. So this is the rate, 10 to minus 4, sort of magical number. You see here very broad windows, how much error can be tolerated. So it's really a powerful method. A number of experimental demonstrations followed because this was nearly 15 years ago. This is in doped solid in Darmstadt in the group of Thomas Halfman. You see a single pulse and then higher order composite pulses. This was demonstrated also by Winnie Hensinger in Sussex with trapped ions. You see the Rabi oscillation here and the composite profile. It was also demonstrated in Hanover by the group of Christian Osbokals, again in trapped ions, and you see here the flattening of the profile. He used it for population shelving when measuring the created entanglement. And we did our own experiments, not only in collaboration with our friends and IBM. Quantum offered cloud access since 2016, and they really changed the game. They made it possible for every theorist to try and prove the theories or the predictions with their online access. They allowed pulse level control. One can control the field entirely until February. This was a very sad day for us when they discontinued this. It's especially true that also in the front end they have phase gates, and they implement them very smartly in transmon qubits by frame change. So the phase gates in IBM Quantum essentially have 0 error and 0 duration. So they are ideally suited for composite control because it's all about the phases. And this is our own demonstration of broadband composite pulses. This is theory, and this is experiment a few years ago. And this is demonstration of the so-called universal composite pulses that we developed in 2014. And this is experiment here on the top, and this is theory, 2D plots, detuning, Rabi frequency. And if you compare this frame to this frame, you see that they are quite similar. And the same applies to everything. So this made us confident that we know what we are doing, and also made us figure out that IBM qubits are quite good if they can reproduce the theory so well. And these are other demonstrations of fractional pi pulses. This is locking the transition probability at various levels. Broadband profiles, narrow band profiles, passband profiles, and here also passband profiles. So this is a toy that we liked very much until February. As an alternative, you also developed a method where instead of the phases, one can use the detuning. So it's a sequence of pulses of different colors. This is different carrier frequency. And you can use the different carrier frequency as control tools in case phases are not available. And as I understand from the same superconducting community, now they are developing another type of qubits, not transmon qubits, but fluxonium qubits. And there the phase control for the moment seems difficult or impossible. And then this could be an alternative. And this is again comparison of theory with experiment with this concept of having different detunings, not different phases. Now I'd like to focus actually on narrowband composite pulses because they are less known and less popular, but they are very powerful too for a few applications. So this is how a picture of narrowband pulses look, the excitation profiles. This is the pulse area, this is pi, the pi pulse. This is Rabi oscillation here. And when you apply longer and longer sequences, you can squeeze the profile essentially to a delta function. So it can be extremely selective. Now we developed also analytical sequences, and the phases are here quite simple. They go as 0, phi 1, minus phi 1, phi 2, minus phi 2, and so on. The excitation profiles are given by simple sine to the power of 2n, and when this n goes up, this tends to 0 unless it's equal to 1. So only the middle survives and the wings are cut off. Now, in the beginning, we did this because we could do, as every theorist will follow a certain line, even if it doesn't have much application. It's like I heard that in 1960 that Myman created the lasers, one of the great inventions of the 20th century. His colleagues mocked him, saying that he discovered something great that uh, solved a problem that doesn't exist. But then problems quickly emerged, and lasers now are such devices that we cannot think about physics without lasers and many other fields. So we had some wonderful profiles, and we even demonstrated them experimentally on IBM Quantum. Here is a theory and experiment, but it turned out that they also have very interesting applications. And this is an extreme example on IBM with 1001 pulses. Is here the yellow profile on the orange, and this is far more than anything that was demonstrated in NMR. The world record before that was a sequence of 81 pulses. We could easily go to even more, but having a profile for 1000 pulses means that also the coherence in the system should be quite good, because you need coherence in order to create these interference patterns. Now, what they can be used for? They can be used really for local addressing. And Rainer Blatt in Innsbruck uses a very simple kind of narrowband composite pulse to really locally address particular ion without affecting the neighbors. And it's a picture stolen from a paper by Immanuel Bloch about optical lattice we saw yesterday and before some talks about it. In one talk earlier in another conference, somebody spoke about quantum pointillism, a term that I heard for the first time, and this meant something like that, picking qubits one by one. Now, this is a simulation of how it would look like using narrowband composite pulses in such a scenario. This is the Rabi frequency profile, essentially the electric field profile of the field, and these are the narrowband profiles that can be created. So if you want to address this ion with such light, this ion will see about 50% of it, and of course you don't want this if you want to be selective, but with narrowband composite pulses you can really address only one of these. One can in principle beat the diffraction limit in a sense, because you can localize your effect much within the focused laser beam. This is an experiment that came a little later in Darmstadt with our support. It's an experiment in doped solid. It's a crystal, and you irradiate the crystal with laser light, focused, tightly focused laser beam. And the crystal has a size of a few millimeters by a few millimeters, so it's a real physical device in space. And this is simulation, this is experiment, this is if you don't do anything, if you just have a single beam, this is your spot. But if you use narrowband pulses, you can see that you can focus the action, not the beam. So you don't focus the beam below, say, 1 or 2 micrometers, but you focus the action. And this is by a factor of about 5. Now they have new results, which I haven't seen yet, but they say they managed to squeeze this to by a factor of 20. And in this manner, you can really use laser beams with a waste of 1 micrometer, but you can have an effect of the order of 20 nanometers or something. So it really works. And it's another application. This is counting single phonons, joint work with groups of Markus Henrich in Stockholm and Christian Rose in Innsbruck. This is vibrational ladder of a trapped ion. This is blue sideband. When you excite from 0 to 1, you also gain a phonon. And the whole thing is that these couplings depend on, in the Lamb decay regime, on the number of phonons. So this coupling is different from that one and that one. And narrowed band pulses really can single out each coupling. You can count the phonons one by one. Now, if you're in the so-called thermal regime, this is the distribution, and you don't need this. You just need one blue sideband, one red sideband, what every ion trapper knows, in order to find an average, the average number of phonons. But if this is non-thermal distribution, this is a method to count the phonons one by one. And this is experimental results from Stockholm. On the horizontal axis is the probed Fox state. They created one excitation somewhere there, a single Fox state, and the vertical axis is the initial Fox state. So they know what they prepare, and then use this method to measure if this is what they prepared. And here diagonal means that indeed they measure what they prepared. And these are sequences of 3, 5 to 11 composite pulses, narrowband composite pulses, and this is experiment, this is simulation. So it works quite okay as well. Now the second part of the talk is going to be a little shorter. It's about dynamical decoupling. Dynamical decoupling is known for some more than 25 years, has been used in quantum computing, but has been known since the 1950s with the Han echo and the CPMG method. So in the dynamical decoupling, you don't want to manipulate your excitation profile, but you want actually to leave the system alone. You apply a sequence of pulses, like here. Actually, they apply many more pulses in order to decouple it from noise, from the environment, from inhomogeneous broadening, and all sorts of unwanted effects. So the ultimate objective of dynamical decoupling is to leave the system unchanged. So the propagator should be equal to the unit matrix. This is the ultimate goal. And this is the famous CPMG sequence of two pulses, pi pulses, divided by interval of tau, and initially we have tau over 2 and tau over 2, and at this point here and at this point the method approximates the propagator with the unit matrix. It's not exactly it. It's susceptible to errors, and that's why there are many other methods developed. CPMG2 is two CPMGs applied next to each other. This is the very often used XY sequence, a sequence of 4 pulses, and the second and the 4 are shifted by pi over 2. So if this is applying the X direction, this is applying in the Y direction. Now, this came a little later after we were so excited about composite pulses, so we decided to put phases on such a sequence, phi 1, phi 2, phi 3, and so on. And we put this in our machinery, and suddenly we developed a sequence of 2n pulses, an even number of pulses, with phases which are given by this simple analytic formula. And in this manner, you can have arbitrarily long dynamical decoupling sequence, because this n can be any even number. And an example of 6 pulses is given here. The second and the fifth have phases 2 pi over 3. This is a sequence of 10 pulses with more sophisticated phases, and so on and so on. And we actually only had one paper on this topic, which came in 2017, but it turned out to be quite successful. So this is simulation in doped solid, praseodymium doped solid in Darmstadt. And this is an experiment, doesn't look quite like that, but you see that it's far better than CPMG or XY4. This sequence of 10 pulses seems to be particularly good. Now, this method is used in about, at least I know about 10 groups on basically everyday basis, in the group of Halfman for optical memories, Wunderlich for ions, Mel-Stoibler for high resolution spectroscopy, and Osborne also for quantum computing, and a few others. And they seem to be quite good. It was the beginner's luck. A couple of years ago, Daniel Lidar conducted a survey of about 60 dynamical decoupling sequences. You see here 60 DD sequence, 10 families, and it's always nice when somebody else tests your sequences. And these UR are the sequences that we developed, and you see they're near the top. Actually, here they're on the top of performance on IBM processor. We lately restarted this, and we studied these sequences even more closely, and we developed more sophisticated sequences that even those sequences that perform very well. Now, the detuning bandwidth, if we're speaking about inhomogeneous broadening, is clearly seen that it tolerates larger and larger Rabi frequency errors. And this is a real experiment on IBM Quantum. The blue curve is CPMG, the classical method that is used. KDD is another very popular method, this orange one. And then the cyan is XY4. And the black one is the earlier from 2017, and the green one is the newest one. You see it really locks the fidelity essentially to 1. And the difference from 1 is the readout error at the transmon qubits. This is against the Rabi frequency deviation, this is against the detuning deviation, with similar conclusions here. So they really work quite efficiently. And you can really freeze your system as it was in the beginning. This is another finding that we found. It's quite often, essentially always, that people keep repeating the same sequence all over again, forever. 10,000 pulses were used in Braunschweig and also in Darmstadt. And we found out in this simple experiment that if you use a single DD sequence, is beneficial than if you repeat the sequence many times. And this is the number of repetitions. The time duration is the same. But in the first case, in the single DD sequence, you simply separate the pulses by a much bigger distance from each other. You have a single sequence from the beginning to the end. And for the same interval, in the second case, you have repeat n times the sequence. And you see that single sequence outperforms the repetitions, and the blue curve is shows what happens if you do nothing to your system. And this is on two different processors of IBM, Brisbane and Osaka. I'll jump over this and I'll finish with pulse shape effects in the last 4 or 5 minutes. The pulse shape effects is also largely related to the phase control, although in a different twist. Now, it's really quite a bit of change of gear. Power broadening is textbook effects that all of you, I'm sure, know quite well. If you measure a spectral line as a function of the detuning, then there is a broadening of the line. If you have larger losses, this broadens the line, but also if you have larger intensity, omega Rabi frequency, when you increase it, here is the power, 5 milliwatts, 5000 milliwatts, the spectral lines broaden. That's why in high resolution spectroscopy, they use as low intensity as possible in order not to power broaden the line. And this is one of the big enemies in high resolution spectroscopy, and this makes measurements very slow. Now, this is in CW excitation. So in pulsed excitation, it has been known for quite some time that situation is a little bit different. It does matter whether you have CW or pulsed excitation. First of all, for rectangular pulses, this is an experiment on IBM Quantum simulation and experiment. And this is Rabi frequency, this is detuning, and we see the same power broadening as in CW. This is pi pulse, 3 pi pulse, 5 pi pulse, and we see how the profile broadens. So there is a linear broadening, which is the same as with CW excitation. Now, it has been known that for Gaussian pulses, there is very much weaker logarithmic power broadening. And this is an experiment from 20 years ago from Klaus Bergmann's group in Kaiserslautern, double two-photon excitation in xenon. And this is for 0.75 gigawatts per square centimeter. This is for 7.5 gigawatts per square centimeter, a factor of 10 more power here. But you see that the spectral line broadens from 235 to 275, not by a factor of 10, but just by 10%. So for logarithmic pulses, there is much weaker power broadening. And now we developed some 10 years ago with a PhD student a theoretical model studying how the pulse shape affects the line width. And we found out that indeed for exponential, there is logarithmic power broadening. For polynomial, however, actually for hyperbolic secant, there is no power broadening at all. But for polynomial pulse shapes, such as Lorentzian, there is power narrowing. Actually, the line width shrinks as you increase the power. And this can be explained by a model, simple model using concepts of adiabatic and non-adiabatic evolution. Now, recently, we did an experiment in this paper with another PhD student, taking a Lorentzian shape and truncating it at different points of time. So this is very strongly truncated at 50%, and this is at just 0.5% of peak intensity. And this is the measured response of the IBM qubits. You see here the typical linear power broadening with strong truncation. And here you see actually power narrowing. Here, this is the pi pulse, 3 pi, 5 pi, 9 pi, and you see significant shrinking of the spectral line. So the effect is certainly there. We try then to push this as much as we can by taking powers of Lorentzian, where this lambda was smaller than 1. And you see a dramatic change and dramatic effect. This is the typical Lorentzian that I just showed, and this is Lorentzian to power 3/4. This is Lorentzian to power 3/5, and this is the pi pulse, and this is the other pulses. And this is the cutoff of these pictures as a function of the detuning. If you look at this picture, this is a pi pulse, and this is 7 pi pulse, and this is a factor of 10 shrinking. So really, this effect exists. And we talked to quite a few people how this can be used, because this is direct spectral observation of the resonance here. And we studied the resolution of this. We found out that it matches the Ramsey spectroscopy resolution, but in a direct spectral measurement. I'm almost done. It turned out here, just to mention that this truncation effects are essential. It very much depends where you truncate your pulse, because this truncation causes power broadening. So this truncation causes this effect, broadening of spectral lines, and the power narrowing effect goes this way. So that's why here we see some narrowing here, but not so much further on, because there is a competing effect. And we pushed this the other way. We made measurements for rectangular pulse, and then these shapes, these funny shapes, and we found the opposite effect, power super broadening. And this is the typical profile by a rectangular pulse, and this is a profile, much broadened profile, which also has some applications, which we can find in the literature. Now, this is our group, Quantum Technology at Sofia University. Quite a few people there, around 30. We have a number of collaborations from around Europe. And I just want to finish by saying that last week we had a conference, in our own conference at the Black Sea, in this place here in Neseber, and this was 16th to 20th of June. The next one is going to be 1 year from now, and watch out. It's a great conference, and quite a few people here have been there, and the response was great. Thank you very much.
Okay, thank you very much. Maybe we have time for one quick question before we move on. Okay, so maybe I'll ask a question from an experimentalist perspective. So could you comment briefly on how this method compares to, say, fully numerical methods that could optimize pulses to achieve spectral selectivity or phase control, putting a control operation on qubits or oscillators?
Yeah, this is certainly not the only control method. Of course, there is the resonant, the adiabatic shortcuts to adiabaticity, inverse engineering, optimal control. The benefit we see here is the analyticity of the results, that you can predict the shapes. Also, the implementation is much easier than, say, an optimal control, which returns some very complicated shapes. Here, what you control are simply a set of phases, so it's basically a digital optimal control, and in this way it's easier to implement. Also, some of the profiles I've never seen in optimal control, like narrow band profiles. Broadband, yes, but not narrow band, and the flexibility seems quite significant here.
Okay, excellent. Thank you very much. All right, so with that, let's thank our speaker again, and we'll move on to our next talk.